Hello, here we are back in my office, and we're going to head into the lab and take some NMRs. Show you how to use the NMR. Okay, here we go. Back in lab. Here's the, oh yeah, here. Your professor's up front reading, doing some grading, it looks like. He looks serious. He's got some big old exit question behind him. And remember, I don't always study OChem. Oh wait, yeah, I do. That's right. Okay, here we go. Let's see, coming by lab. Oh, look at this, look at this. We got a little graffiti here about base strength. Look at that, it's base strength based on size, resonance, electronegativity. Pretty cool, huh? Coming soon to a OChem virtual lecture near you. Retrosynthesis, that's coming up. Okay, now back into lab. Well, we're in lab, but back into the NMR. So here's our IR spectrometer. We've worked on that, right? There she is. And then the NMR is over here. Here it is. This is the computer that runs it. And here is where we're going to put our samples in here. It's pretty cool. It floats on air. You'll get to see it shortly. We'll use this inject, eject controller. And here we go. Hey, Sydney. Hey, Cassidy. Yeah, they're over here. Sydney and Cassidy are protecting the polarimeter. We'll learn about that later. But over behind us, we're going to go and prepare our samples for the NMR. So the two samples I'm going to train you on are ethyl acetate, and we're going to make that sample very concentrated. So ethyl acetate. We're going to make it approximately about 98% ethyl acetate, or do I say 95% ethyl acetate, and about 5% TMS. Currently, this, you can see it's dry. Probably just got residual nothing in there because it's slowly evaporated out of the cap of the NMR tube, but that's no big deal. We'll just add more. The way we're going to do it is I'm going to add first TMS just a little bit, and then the ethyl acetate up to about 4 centimeters. So let me show you how to do that. So I just laid my empty NMR tube down next to a ruler, and I mark it at about 4 centimeters with a Sharpie, and I want to fill up my total volume to about there. It can go down to like 3.5 centimeters, that'd be okay, but below that, it's gonna give you problems. Above it's fine, but it's just wasteful. If a sample is only about 3 centimeters high in an NMR tube in our NMR, the spectra will come out looking really strange. You have a lot of extra signals. It's easy to fix. You just have to add more sample. And the reason why is because the radio wave pulse will be traveling through your sample solution and air. So it'll look like this. So let's say this is an NMR tube, and you've got some sample in here, and it's less than 3.5 centimeters, then our radio frequency generator, got a big one here, when it's pulsed through the sample, it'll be hitting your sample, but also this air up here. So now it's getting a spectrum of air and your sample. It's going to come out weird. So yeah, you don't want to do that. All you got to do is just add a little more, and I say 4 centimeters to be safe. 3.5 is okay, and that's it. Here's our TMS. We're going to add that first. We just need a little bit. Remember I said I was only going to add about 5% of the volume will be TMS. Just need a little bit to see it, so I can set that to 0 as our reference. So I'm going to take my NMR tube and open it up. Got to be careful taking these caps off. Kind of just jiggle them and be slow about it. If you try to yank them, you can break the NMR tube. But okay, I got my cap off. And then I'll take my TMS, and when I open the vial, I want to be careful. It's very volatile, and just open it slowly. The first time it might vent. It didn't this time. And then when I pipette it up initially, it's going to be very drippy. So here, this is my TMS. Watch what happens. I got my pipette bulb here. As I draw it up, it's going to drip. Look at that. I'm not squeezing the bulb. It's just, that's doing that on its own. So I'm going to push it all out, and then I'm going to do that again. What I'm doing, you could think of it as maybe conditioning the pipette, but it's not really conditioning. It's more like I'm cooling the pipette. The pipette's it's cooling by evaporation, evaporative cooling. And as the pipette cools, then it has less of a head space gas pressure pushing it out. So I always like to And when I first get a real volatile solvent like this, draw it up, spit it out. With a clean pipette, of course. Draw it up, spit it out, draw it up, spit it out. And then it'll be much more manageable. So then I'm gonna take my pipette, my NMR tube and my pipette, and I'm gonna just try to put a little bit in there. And watch at the bottom, it's gonna be, take a little bit. Oh, do you see it dribbling down? That's on the inside. Yep, that's more than enough. And so I've got my TMS in here. Always start with the TMS because then you can tell how much you got. If I had added accidentally like triple this, I can just pour some out. Next up, the sample, the ethyl acetate. I gotta go grab it actually, forgot to grab it. Okay, here's our ethyl acetate. It's clear liquid. You see it there, I drew the structure on it. Maybe you can see it, my hands are blocking the back there. Ethyl acetate, and we're gonna get this out and fill up our NMR tube to that 4 centimeter line that we made earlier. It's kind of hard to see on here, but the 4 centimeter line is about right there. And so when I first open up my ethyl acetate and take my pipette and put it in there, the first time I draw some up, it's probably gonna drip a lot, watch. Actually, it's not too bad. I guess it's not too warm, this pipette, but I'm gonna still draw some up and put it back just so I can evaporatively cool the pipette so it won't drip on me too much. And now I'm gonna try to fill this up to about the 4 centimeter mark. Here we go. Pretty good. Let's see, maybe a little drop more. So yep, there it is. It's right about the 4 centimeter height. And I'll cap it and shake it up. Not vigorously, just kind of invert it a couple times. And I'll have myself an NMR tube ready to run. It's got the internal standard TMS in there to help it, to give me something to set to 0. And then all my signals for the ethyl acetate will be based off of that. Okay, looking good. And then I made this nice little like paper card to identify it. I want you to always do this if you take NMRs. You don't have to make a fancy printed one. Just take a square of scratch paper, write on there your name, the structure and everything, put a hole in it, and then you can have it nice and labeled like this. Okay. And before we run the sample, one thing we always want to do, just like on IR, we want to predict what the spectrum's going to look like. If we have an idea before we get in there what it's going to look like, our chances of making a mistake are a lot less. So I always want you to draw out the molecule twice in this case. Predict the proton NMR and the carbon NMR, then you run it and you look for those peaks you want. Okay, here I go. I'm going to predict this one. I'm going to draw it out once for the proton NMR. And when we run this, we're always going to do proton NMR first, because we'll easily be able to see our TMS and set it to 0 because it's a stronger signal in proton NMR. So this will have, here, I'll use some colors. Here I'm expecting a 3 hydrogen singlet, and it's alpha to a carbonyl, so I'm thinking, oh, about 2 parts per million. Then over here I'm looking for the 2 hydrogen quartet, and that should show up about 4 parts per million, being alpha to the oxygen. Finally, I should have a 3 hydrogen triplet. Triplet at about 1 part per million alkane range. And also, let's not forget, it'll have TMS, so I'll draw that out. So TMS should look like that, and have, that's tetramethylsilane, a 12 hydrogen singlet. At 0 parts per million, because we're going to set it there. Should be close to 0, but it might not be actually all that close today because we haven't used the NMR in a while, but we'll get it to 0. Next, we'll do the carbon NMR. Okay, for the carbon NMR, I should have a 1 carbon signal there, and it's going to be proton decoupled, so it'll be singlet. And it should show up, I don't know, about 20 parts per million, maybe 25 parts per million, alpha to a carbonyl. Then we have a carbonyl signal. The carbonyl signal has a group attached to it that can resonate into it. It has a lone pair there. So this one's going to show up, I don't know, 175 parts per million, 180. not all the way down at 200, like a ketone or an aldehyde without a lone pair. Then here I've got a alpha to oxygen, so maybe 55 parts per million. Oh, sorry, my handwriting. And finally, this one here is more of like alkane region, maybe 15 parts per million. And the TMS, we might not see it because there's not a lot of it. Sorry, my colors aren't that great on this one. The TMS, there's not a lot of carbon-13. There's only like 1% of the time, 1.2% carbon-13, right? And when we made up the NMR tube, there's only about, what would I say, 5% approximately of the volume is TMS. So, man, my handwriting. So if I only have a 5% TMS volume in there, and of that 5%, only 1.2% is carbon-13, that's going to be a pretty low amount of carbon-13. It's going to be 5 times 0.012, which, my calculator's on my phone that's recording this. A low number, right? And so the odds are we won't even see the TMS in the carbon-13. But we'll see it in the proton NMR because, proton NMR, the H1 isotope, that's like 99.99% abundant. And so and also the sample is like 95%. Oh no, it's not. 95% the sample. Sorry, no. But it's 99% abundant. So even though it's 5% of the sample, almost all that 5% is there. So we should see it. So here's our NMR again. Initially, it's asking for a password to get into the software. It's simple. I have it up here. I have all your main commands on top of the printer. I used to have like a guide to this where it would give you step-by-step instructions, like a choose your own adventure, but it seemed to be more confusing than it needed to be. So now I just have your main commands, and I'll explain those. But first off, there's the password. It's Anasazi. It's a company that we bought the NMR from. A really good company. So it's A-N-A-S-A-Z-I. So let me enter that. A-N-A-S-A-Z-I. See what happens. It should start right up with the two programs that we're going to use to run NMRs. We use one software to the one that just popped up. One software we use to collect kind of like the raw data. We'll usually view it as the FID, the free induction decay. And then after we collect that data in this software, which is called AII PNMR, that AII is Anasazi Instruments, right? And PNMR, Pulse NMR. And so we're going to run it. We're going to run our spectrum with this software. Run our sample with this to get what's called like the crude data, I think of it, the free induction decay. Then we're going to process it over here in this program called NUTS. It's got the NMR symbol, NUTS. So I click that and that'll open up. And then this program, it's called NUTS for a good reason, because it'll drive you nuts. It's a little bit interesting. The logic of this software is kind of the opposite of the other one, but we'll get the hang of it. I'll show you. Okay, let's get our sample in the instrument and running. The first thing we need to do is get our NMR tube we just prepared on this spinner. It's this guy right here. It's a plastic piece of equipment that we'll use to hold our sample. We don't really want to touch it much. You notice I'm using a chem wipe. I could touch this part. I don't want to touch it too much, but I don't want to touch the thicker end of it, because the thicker end of that needs to spin inside of this metal tube right here. We're going to put our sample down into this metal tube, and air will make it float and spin in there. Its spinning will be hindered by friction between this plastic and the metal tube's walls. And if we get our fingerprints on this and our oils from our finger on that, they get the oils inside of the tube, and then the tube picks up dust. It sticks to the oils in the tubes, and then your sample after a while won't spin. If it doesn't spin, you can't get a good NMR. So we want to keep it nice and clean. So we always want to like hold this with a chem wipe when we're using it initially before we get it in there. And you'll see it's got like the thicker end there and then the thinner end, right? It has to go in this way with the thick end up. If you can't put it in upside down like that. You should see on the top, I usually have markings like that black Sharpie marker there. That's the top. You'll get the hang of it. Okay, so now I have to inject my NMR tube into this. So I'm gonna have to hold the camera differently. Okay, here I go. I'm gonna grab my sample. Remember, this is the ethyl acetate we just prepared. I'll remove the card from it. It's at about 4 centimeters height, the total volume of TMS and ethyl acetate. And now I'm gonna take my spinner and I'm gonna put the sample through the thicker end, like that. And now it's important to put this NMR tube to the right height. If I just have it right there, it's not gonna spin. If I have it too far up, it's not gonna spin. I have to have it just right. So how do I do that? I have this right here, this little depth gauge on top of the NMR. I just stick my sample right there and I carefully push down and eventually it'll hit the bottom, and that's the height it should be at, right there. I'll show you again. So if I have my spinner lower like that, I just stick it in here, just carefully shove it down like that, and once it stops, I feel it stop, that's the height it should be at. And now I'm gonna put it in the NMR and hope it spins. Sometimes getting the sample to spin is the most challenging part of running an NMR, but lately it hasn't because we got a new spinner and a new air supply, so let's see how it goes. Okay, so the way this is gonna spin is when I put it into that metal tube I showed you, there's gonna be air blowing up at it, and it's gonna hit the little beveled part of the thicker plastic, and that's gonna make it levitate. And then there's gonna also be some air blowing sideways to spin it. And it has to have the correct balance of levitation and spin to spin well. If the air from below is too strong, it'll pop up out of the range of the radio waves that needs to have passed through it. And if the air spinning this way is not strong enough, it won't spin, it needs to spin. So you'll see when I put it in here if we can get it to spin nice. Okay, here's our air source. I'm gonna power it on right here and you'll hear it. You hear that? You have to hear that, and when you hear that, then you come over to the NMR metal tube here and you set your sample there and watch, it'll float. Kind of cool, huh? So there's air blowing up on it. We want it to sink down into the tube, and then we want it to start spinning. So the way we're gonna do that is we're gonna come back over to our air controller here, and I'm gonna hit the off button on this to stop the airflow up so it can sink down. So I haven't done it yet, haven't done it. I'm about to do it. Just believe me, I'm about to hit it and you'll hear the sound stop. So ready, set. So then the tube drops down in there, and if you can see good enough, you can see that it's not spinning yet because, well, let's see if we can focus on it. If we can focus on it, you'll see that you can read the numbers or impressions on the NMR cap. It's a little bit hard to see right now. It doesn't want to focus down there, but it's not spinning currently. But when I come back over to my air supply and I power it back on, it'll start spinning, hopefully. Let's see. 1, 2, 3. All right, I was lucky. First try, it's spinning good. If it's not spinning good, it's okay, it happens. All you have to do is eject the sample. So I'll show you how I do that from another camera angle. Okay, if it's not spinning, what you need to do is just eject it. This red button that says eject is the eject button. But before you press it, you want to make sure you've got a chem wipe over the metal tube, because when you hit eject, it's going to pop up. And we want it to not pop up and out and maybe fall and break. We want it to run into our finger. It doesn't pop up very strongly. It won't hurt your finger or anything. But you definitely want to stop it before it pops out. So you just hold a chem wipe over this, and then you just press and hold eject for a second. And then you'll feel it right there. And there it is. Oh, it kind of sunk a little bit, but it should come back up. No, it didn't. Let's try it again. I think I could just grab it at that point too, but there it is, see? Pretty cool, huh? And then I can grab it out, and I might need to adjust the height of the spinner, because remember how the spinner height is important, I said? So let me see, mine was already spinning, but if it weren't spinning, I might pull it out, lower the spinner like I just did, bring it over to the depth gauge, get it to the right height, bring it back over here, spinning, And then I hit the power off button. It drops all the way down. Hit power on again, and I'm gonna check and see if it's spinning. It's spinning again. It's looking good today. If it's not spinning for you, then just, ask a friend for help, try a few times, and then call me. I know some tips that I'm not gonna teach you because they're kind of dangerous for the machine, not for you, but so I don't wanna advertise those, but other people in your class will be good at this. That, whatever reason, it's like a luck, confidence thing, and they're like, oh, you need help with spinning that? I can spin it, I can get it. I'm the spin doctor. If you want to buy me flowers, just go ahead now. And if you want to talk for hours, marry him or marry me. I'm the one who loves you, baby, can't you see? Ain't got no money or family tree. Okay, enough of the spin doctors. So now I've got my sample in there spinning. I'm gonna come over to the software and run it. Okay, here's the commands I was telling you about. We're using two software. We have this AII software. That's the AII PNMR software. These are the main commands we need, just these 1, 2, 3, 4, 5, 6 mainly. And then we have the NUT software. That's where we're gonna process our spectrum, make it do a Fourier transform, do integration. So we got some commands for that. So when you're doing stuff, just look up here if you don't remember the commands, because we're going to use commands to run this. It's much faster than a mouse. I heard an interview of the person who invented the mouse, and he was saying it's pretty inefficient. He wasn't happy about it, because like if you look at my screen, if I want to like say go to do something like file, open or something, I have to move my mouse over there, I have to click on it and then find it and click on it. Where if I just do the shortcut keys, command whatever, it's much quicker once you learn all the shortcut keys. So that's how we're going to run this sample too. So I'll show you how to do that. The first thing you always want to do when you put a sample in there is run a proton NMR. Always do the proton NMR first, because the proton NMR serves a number of purposes. It serves the purpose of giving you the TMS signal to set to 0, and also to see if your sample needs to be shimmed. Let me explain what shimming is. Okay, so first off, let me describe what a shim is. You probably heard the word shim before. A shim is something that can help balance things. So let's look at like a chair. We can shim this chair. You've probably seen this at like coffee shops and stuff when you were allowed to go to them. So see how this is a little off balance? Like this leg and that leg are not perfectly on the ground. I can rock it back and forth. I can try to fix that with a shim. I'll show you how to do that. This is my fancy shim. It's a piece of paper towel. Fold it up a little bit, and if I put that under one leg, it's like it's acting as that leg is longer. So now the legs are balanced, and when I try to rock it, it doesn't. It's shimmed. So shimming just means to adjust the piece of equipment like this chair or your NMR's magnetic field in our case, so that it's balanced. Okay, so imagine this is our sample in the NMR. If the NMR's got this main magnet, the strong magnetic field applied to it, and the sample's spinning, and you want to have the same exact magnetic field strength at the bottom of the tube, the middle of the tube, and the top of the tube. Because if they're not the same strength throughout, then a signal down here, which should be at like 4 parts per million, it might be at a stronger magnetic field than the same molecule in the middle, and now it's at 3.9 parts per million, and then at the top, maybe the magnetic field's weaker again, and it's at 3.8 parts per million. So now instead of having a nice sharp peak at 4 parts per million, it's widened and it's not as defined. So you want to have what's called a homogeneous magnetic field strength throughout your whole sample. So I want the magnetic field strength to be the same down here, 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 and there, right? So how do we do that? We have our NMR's magnetic field, the main magnet, and there's also little electromagnets around it. And when we shim, what we do is we tell the machine to tweak the little electromagnets and then check the sample to see that the magnetic field strength is the same throughout. So all it really does is it looks at one particular peak and it sees if that peak gets sharper when it adjusts a little bit of this electromagnet, adjusts this a little electromagnet, this one. Just kind of tweaks those electromagnets so that it gets the magnetic field as homogeneous as possible throughout your sample. And then we say our sample's shimmed and we'll get good signals. Usually you don't always have to shim. You usually have to shim if you go from like a concentrated sample, like the one we're gonna run is ethyl acetate. It's 95% ethyl acetate, it's concentrated. So for that one, we're gonna we're gonna shim on it, and then we're gonna run another sample, a dilute sample of toluene. When we do that, you'll see we'll probably have to shim. Whenever you change concentrations greatly between samples, you usually have to shim. No big deal, you just tell the machine to shim, so we'll do it now. All right, we talked about shimming our sample, which I'm pretty sure we'll have to, but before we do, let's run a proton NMR and look at it and see if it suggests we need to shim. You should always just run the proton first, see if it needs to be shimmed. How do we do that? We first make sure we're in the proton NMR settings. Here it's the command for that is NU space H1. If that'll get you into proton NMR. When you want to take a carbon NMR, you have to type NU space C13. So let's see what we're in currently. I'm going to come over to our screen here. This is the NUTS program, which I'm not ready for. I need to first collect the data, the raw data, and the AII PNMR. As I look down here, you'll see it says H1 right there, the cursor. That means I'm already in H1 NMR, so I don't have to change it to that yet. I'll show you how I would change it though if I needed to in a second. And then here's some parameters you see, like we're going to be doing the receiver gain. The receiver is at 3. We'll see what that means shortly. Acquisition time, pulse width. We're going to pulse all the radio waves for 18.5 microseconds. Nucleus H1. This is 60 megahertz NMR. Yeah. Okay. So let's come over here. I'm going to switch it to carbon NMR just to show you how it works. So if I want to switch to carbon NMR, I have to type NU space C13. Then if you come over here, you'll see I'm typing that into the command line down there. Sorry. Wow, that's bright. Okay. But nothing's happened yet. In this software, for things to happen, you have to hit enter. You have to tell it after your command. So you have to say, okay, I'm ready, enter. And now when I did that, when I come over to my software, it had changed. Now it says C13, it's no longer in the H1 setting. And you'll see over here, it's doing, it's set to do 12 scans now, not 1 scan, because carbon 13 is less abundant. And it's the carbon 13 nucleus. And our frequency now is 15 megahertz, not 60 megahertz, because carbon 13 absorbs lower energy radio waves. Okay, but that was a waste of time because I want to run the proton NMR first, right? But I just wanted to show you how to do these commands. So for proton NMR, I have to come over and I have to hit N U space H1. Where's H? H1. Okay, and now did that happen yet? No, because remember this software you have to hit enter for things to happen. So it's still like just saying NU space H1 until I hit the enter key. And look at that, I'm back in the HNMR setting. There it is, over here. H1 NMR 60 megahertz, looking good. All right, let's run this. How do we run it? The command we'll use the most is ZG. Think of it as zero out the old data, go get new data. So we have to just type ZG. These are old commands. I think these are like maybe German-based words from the original NMR. Just a lot of this NMR discoveries in Germany, and then advancements in the US. Okay, so let's see. Maybe it was Austria. I should remember. I just made you guys do all that spectroscopy intro. All right, here we go. ZG. So there's Z, and then G right here. Okay, did anything happen? Nah, nothing happened, right? Because I haven't hit enter yet. So I have to come back and I gotta hit enter. After I hit enter, it's gonna ask me what I wanna name the data I'm about to collect. It asks you before you collect it. So what do you wanna name it? We're gonna always use the default name like we did with IR, and we're just gonna keep saving over it so it saves the computer hard drive, because we're gonna print our spectra anyways. So I'm just gonna come over here and I can click on save right there and it'll start scanning, it'll start pulsing. But instead, I'm just gonna hit enter, either way works. So hit enter, boom. And now you'll see here it says running ZG. When the FID is shown in red, the receiver gain is too high. We'll see if that happens. I think that will happen because I think, yeah. So that's our FID, our free induction decay. Not quite red though, huh? So what's happening there is our sample was pulsed with all the radio waves. The detector was off initially. The unabsorbed radio waves passed by the sample. Then, after they pass, the sample starts to relax and release radio waves. and as it's releasing them, the detector turns on and detects them. And once the detector turned on, when it turned on after it was off in the beginning, that's like time 0 there. It turned on, a bunch of the hydrogens were relaxing, and as they were relaxing, all these frequencies are coming in. And then over time, less and less are relaxing because they're all pretty much getting to ground state. And it took maybe like a little less than 3 seconds, or 2 seconds about, for them all to relax. So that's how long it took. And then that data was collected. So this data is in the time domain. So we need to now do the Fourier transform to turn this into the frequency domain. That's easy enough. We're going to do it this way. We're going to go over to the NUTS software. So that's this one here. NUTS. Click on that one. Here's our NUTS software. And we're going to use commands for this too. How are we going to bring over that data? We're going to look over at our sheet, our cheat sheet here. We have the NMR commands. We already looked at those. Now we're in NUTS. The command to bring it over, the HNMR, FID, and Fourier transform it, is the letter A and the number 2. Simple. We'll bring it on over. And you notice there's no enter for this one. So this is where it's opposite the software. I just have to hit the letter A and the number 2. When I do that, it automatically brings over the spectrum, and oh my goodness, that is great, huh? Look at that, right on. Hold on, let me grab my piece of paper, our predictions, you'll see. Okay, so we had predicted the most downfield signal would be this two hydrogen quartet. Do we see a 2 hydrogen quartet? Looks kind of like a 2 hydrogen quartet to me right there, huh? And then we would have a 3 hydrogen singlet about 2 parts per million, and a 3 hydrogen triplet about 1. So we should see a big singlet and a triplet. And there it is, yeah, there's our singlet and there's our triplet. Okay, and then what's this other guy over here, this singlet? What's going on there? That's our TMS. Is our TMS at 0 currently? No. But can we fix it? Sure. Yeah, easy. That's what we'll do next. So to fix the TMS, to set it to 0, we go back to our AII software. And you'll see there's a command here, FO, frequency offset. We're going to use that to set TMS to 0. But first, I need to know exactly where it is. So an easy way to do that is to bring your mouse, I got my mouse here, and left click, the normal click on the screen. Here's my cursor. If I left click and hold, I get this crosshair. And then if I move my crosshair up and down the horizontal aspect of that red line, the horizontal red line, wherever I put that, I can say, hey, tell me about the placement, the parts per million of everything above that red line. So right now, if I ask the software to tell me everything above the red line, I'd only get the 1 singlet there, right? If I go here, I'll get 2 signals, 3, 4. So let me show you. I'm gonna go do that with the keyboard. Oh, how do I do it actually? As I'm, right now, I just let up, so there's nothing on the screen, right? I have to click and hold left click, and that's when that cursor's up. And then while that's occurring, I have to hit the letter M on the keyboard for minimum peak height. So let me do this, it's gonna be a little awkward. So this is the M, boom, I just hit M. And then as I come back, you see it made a little tick mark, and up above, it's telling us that those are at 3 parts per million and 2.259 parts per million. Okay, so why do I tell you this? Because I want to know precisely where TMS is. I didn't go low enough, so I just have to move this horizontal line down lower. And when I get there, now TMS is going to show up. It's poking above the horizontal line. I just re-hit the letter M again. And now it's showing me that one. And when I go up, it looks like TMS is not at 0. It's at 1.058 parts per million. So I have to know that because I want to tell the other software to move it over. Let me just show you a little bit more with this minimum peak height thing. One other thing too. The wheel of the mouse, this wheel right here, if I roll it, I can make the peaks smaller or larger. Like watch. See, if I roll it back, they're getting shorter, huh? And then if I roll it forward, they get larger. So I can adjust that. And then when I click, and click and hold, if I bring my cursor all the way down into here, into the what we call the baseline down there. If I hit M, let's see what happens. Whoa, that's ugly. What it did was it labeled every little peak in the baseline. got like, whoa, that's just too much, right, going on there. I don't want that. So all I need to do, it's easy to correct. I just take my cursor and I make that horizontal line again at a reasonable height, not too high, like there maybe, so I get all this. And then I type the letter M, and now it's only showing me the signals that are above my horizontal cursor. Let's look a little closer to it, that baseline. That's an interesting thing. So these are signals, right? They're clearly signals. This is the baseline. If I zoom in a bunch, you'll see things will start to show up. See, we got some stuff going on here. See all this little jagged? That's called noise. That's just random up and down, where these are signals. They're much stronger than noise because noise over time cancels out. Well, there's only one scan here, but one pulse. But you can cancel out noise with more scans depending on the instrument. And then your signals, but ours is so good. It looks awesome, huh? All right, so but let's get back. I want to correct TMS here. So it's at 1.058. Okay, now I'm going to come back over to the AII software. It's right behind the NUT software here. Sorry about the blurriness. Okay, here we go. I'm just going to click on that. So now I'm back on my AII NMR software. I'm going to come down and I'm going to type the command FO. So on my keyboard, watch how it happens. I'm going to type FO, frequency offset. Nothing occurred yet because I haven't hit enter. I hit enter. There it is. And what does it say? It says enter current position of the reference. So the reference we're using is TMS. It's currently at 1.058. And then I'll click OK or just hit enter. Next question will be enter desired position of the reference. So now desired position, where do I want TMS? 0. I hit OK. So now the TMS has been adjusted in this software, but it has not made any changes to the NUT software. See how it's still not at 0? So what I need to do is I need to recollect this FID, a new data collection, because with the new frequency offset change I made. Oh, easy enough. How do we collect the data? Once we're in Proton NMR, we type ZG, 0 go, and enter. I'll show you what I do. I type 0, Z, G, and then I hit enter. And when I hit it, the dialog comes up and asks you want to use the default name, and I just hit enter again to say yes. So you're going to get quick at this if you get to use it. You'll come in, you'll just hit ZG, enter real quick to like get the scan going. So it's doing its one pulse right now. We're just waiting. Oh, there it is. See how it came out red this time? What that's telling us is the receiver gain's a little too high for this concentrated sample, meaning like, imagine you had a hearing aid and you turned it up really loud because you couldn't hear somebody, and then another person came in and started talking really loud, so you would hear it, it would hurt your ear. You would turn down the receiver gain in your hearing aid. That's something that's happening here, but it's not that big a deal. Okay, so I rescanned this. So when I go back to NUTS, I go back to the NUTS software, it'll still be the old spectrum because I haven't brought over this data. I got new data to bring over though. How do I bring it into NUTS? I come back over here and I notice the NUTS command. Oh yeah, it was the letter A, the number 2. And like I said before, you don't have to hit enter for this. So I'm going to do it on the keyboard and you watch. Believe me, I hit the letter A. Oh, actually, you can see it there. There's the letter A, right? And now the number 2, right when I hit 2, it brings over the data. And look at that. Oh, nice, right? TMS is much closer to 0. Let's see how close. Remember, if I right click and hold, I can get this crosshair, and now I can have it at the height of the TMS, and I just have to hit M on the computer. Currently it's showing the old numbers still. They should have probably erased, but that's not what we want. But when I hit M, it'll give me a new values. Oh, and look at that. Oh yeah, it's a little bit weird. It's showing the TMS as 2 signals, but they're close to 0, huh? Let's go look at that. Why is it 2 signals? The reason why is this sample, it's shimmed pretty well. You probably don't even need to shim it, but we'll shim it just because we're learning, and because TMS has 2 signals on it. We'll see what that means. So how do we get a closer look at this? So what we do is you take your cursor and let's follow my cursor. See how it says here base level? We're in the base level currently of the NUT software. there's other levels above this. So the level above this we want to go to is the zoom level. The way you can get into zoom easily is just double click anywhere on this screen, double left click. So here it is, watch, double click. See how the crosshair appeared with ZO? So I'm in the zoom mode right now, and it says zoom right there. I'm no longer in the base level. All right, how do I zoom in on things? I click and hold and I drag over it, and I got that pink area, and then if I right click, it'll zoom in right on that area. Look at that, that's a pretty quartet, isn't it? Right about 4 parts per million. Okay, so I'll bring it down again. And then if I want to come back out of that zoom, I right click again and I'm out. And then I right click again and I'm in. And then I'm out. And then I'm in. And then I'm out. And then, why would I want to go in again? Just kidding. All right, so let's look at our singlet here. Drag across, right click. Oh, it looks nice and sharp. That looks really good. And then I right click to get out. Go look at the triplet, drag across, right click. Oh, this one's really good. A little funky there. Not bad. Right click back out. And now TMS. I think this TMS is going to be a little strange. Let's see. Right click in. Oh yeah, see how it's a doublet? TMS should not be a doublet, right? What's going on? What this tells me is that I should shim. Well, you know, practical sense, I don't need to shim right now. This is pretty good, especially because my TMS is just set in my 0, right? And these look really good, so I don't need to shim, but I'm gonna shim because we're learning. So, and also if we didn't need to shim, we wanted to print it out or something, we'd zoom in across all the signals, so get them all on the screen like that. Okay, but what I wanna do now is shim, so I'll show you how to do that. It's easy. Oh, another thing too, we're in the zoom level, right? We're not in the base level. You often wanna get back to the base level to do other things. How do you do it? Easy enough. In Nuts, all you gotta do to get out of things is hit enter. So I hit the enter key once, come back over, and now I'm in the base level. My cursor doesn't look like a crosshair. Okay, but let's shim. So we do the shimming within the AII software. See where it says shim there? And then, that's the command. We're gonna type shim and then enter. And then we're gonna come over here and we're gonna hit, for relaxation delay, 2 seconds, and we'll start it. So let's do that. So I'm gonna come back over. This is the Nuts software. I don't shim there, I shim in the other one, the AII software. So I'm gonna move my cursor over here and select that one. It's got the FID there, right? I'm in the AII PNMR software. Come down and I'm gonna type shim. So watch as I type it on the keyboard. I type S-H-I-M. Easy enough, right? Oh, sorry, I was covering it up. I type shim there. Nothing's happened yet until I hit enter. There we go. And now it's asking me about the relaxation delay. It's 2 seconds. And then I hit enter. And it'll start shimming. Shimming, remember again, it's adjusting the, well, it's going to first adjust the receiver gain. And it's adjusting the electromagnets around the sample to try to make the magnetic field as homogeneous from the bottom to the top, all through the sample. So it's shimming the C and Y electromagnets, and it's pulsing through those. And the relaxation delay I was telling you about, that's the time it gives after a pulse, the sample to relax, to make an FID, and then after 2 seconds, it pulses again, and then it makes the FID, and it pulses again. And that is actually gonna be set. It might change. So we set it to 2 because that's just normally a pretty good value. We'll see after it's done shimming. It might change. It might not be 2 anymore. Okay, so shimming could take a minute or 2. Not too long, but if you have a sample in NMR and it doesn't look like it needs to be shimmed, like this one didn't need to be shimmed, don't shim because it just takes time. If it does need to be shimmed, yeah, definitely shim it. Because if we hopefully got in here in the spring, it'd be great if we can come in the spring and you guys can use the instrument. There's only one NMR, so I don't want you to spend time shimming if you don't need to, because then other people can get in. Okay, and when it's done shimming, it's not very obvious. It just stops the pulsing. So, oh, and let's see what the values are at now. Oh, so now the receiver gain, it was at 3 before, now it's 1. So it turned down the receiver gain because we have such a concentrated sample. And I put in there to have it do a relaxation delay of 2 seconds, but it adjusted it to 3. 2 was just like an initial guess. All right, so now we need to rerun the sample again, because now we've shimmed it. We've set TMS to 0. We're gonna rerun it. So how do we rerun it? Easy. The command we use over and over, ZG, enter, enter. So here we go. Come down. I'll show you on the screen here when I do it. I hit, make sure it looks pretty good. Okay, I'm gonna hit ZG, enter first, and then the default name, enter again, and it'll start scanning. This stuff becomes very quick as you do it more. You come in and you're just like, get the sample spin and ZG, enter, enter. Shim, TMS. Okay, it's done. There's our FID. And notice how the FID is not so big. It was bigger before. That was because our receiver gain was lowered to 1. Okay, now back to nuts. Let's go nuts. This is still the old data. How do we bring in the new data? We come over to our cheat sheet. Oh yeah, it's the command A2, letter A, number 2. So I'll let you watch me do it. It's gonna be down here. I'm gonna type A, and then when I hit 2, it just automatically happens. I don't have to hit enter or anything. So there it is. From this perspective, it looks about the same. Let's zoom in on TMS and see if it got better. So remember the TMS was a doublet. And how do I zoom in on it? I'm in base level right now. I just double click anywhere. Now I'm in zoom. It says zoom there, right? I drag over TMS alone. I right click. Oh, and look at that. Nice and sharp. Woohoo, looking good, huh? I like it. Okay, and then once I have everything where I want it, actually I'm gonna get back out of the zoom level. So that's zoom there. I'm gonna hit enter to get out. I'm on base level. I'm gonna see where the TMS is. I'm gonna click and hold, and I'm gonna type the letter M. Yeah, TMS is a little bit off. It changes, it fluctuates over the day. So remember it was closer to 0 before, now it's 0.112. We can fix it again. We don't have to, it's close enough, but let's practice, let's do it. So to fix it, we go back to the AII software, and the command is FO, frequency offset. So I come over here, and I type F9, no, F0. Enter. Oh, wow. Enter. And then it's asking for relaxation delay. It picked 3 last time. Oh, I'll just say 2 every time. You could put 3 there. It doesn't matter. It's just the first guess. Oh, wait. No, that's the relaxation delay. I hit the wrong thing. Let's say 0. I messed up. Oops. This will be good practice. This is TMS, not relaxation delay. All right, so anyways, I just moved the TMS poorly. That's okay. We're going to learn. Let's just rerun it and see where it's at. So I go ZG, enter, enter. Okay, so now it's going to be pulsing all the radio waves. Detector's off initially, and then it turns on as it relaxes, and we'll see a bunch of hydrogens relaxing initially, and then less and less and less and less. And we'll go over to nuts. And this is the old data, but as I type the letter A and the number 2, the new data comes over, and look at that. Yep, I moved TMS over to a negative value. So there's 0, there's a triple letter 2. That's okay, I can find it. I click and hold, and I type the letter M. Got it, right? I come up, where is it at? It's at negative 1.804. Okay, so I'm gonna go over to AII software, and then type my frequency offset again. F0, enter. Okay, where is TMS right now? This is key. I'm kind of glad I did this. You have to make sure you hit the negative. If you don't hit the negative, this isn't going to work. So what was it again? I forget already. Was it negative? Yeah, it was negative 1. Negative 1.804. All right, let's go back. So here I am right here. Negative 1.804. Enter. And where would we like TMS? 0. That's reference, right? Hit enter. Okay, so now I've corrected this software, but I still need to collect new data to bring it over to nuts. So let's do it. Sorry about the shakiness of this. I'm gonna have to type ZG, enter, enter, and it's gonna pulse all the radio waves. Detector's off. Hydrogens are excited, then relax. As they relax, the detector comes on. You get that free induction decay, FID. I go back over to nuts, and the command to bring over this new data is the letter A and the number 2. And look at that, we are all good now. Now our TMS is back near 0. If I click and hold the horizontal cursor there, and I type M, Where are we at? Oh, close enough. 0.065. It's good to me.